All right, welcome to section 4.2. We're going to be looking at something called the mean value theorem. The mean value theorem. Okay, so we actually look at the mean value theorem later on in this section. We're going to first consider something called Rolle's theorem. And we use Rolle's theorem to prove the mean value theorem. Okay, so let's start with Rolle's theorem. We're going to require a few things for this. So we're going to let f be a function. That satisfies three hypotheses. And we'll draw a picture too, because this, again, chapter 4 is a very visual, very graph-oriented chapter. Okay, so number one, we want f to be continuous on a closed interval, just like we were doing in the first part of chapter 4. So f is continuous on a closed interval AB. All right, the second thing is we want f to be differentiable. On the open interval AB. And then the last thing is we want the endpoints to be equal on the function. Okay, so let's see if we have these three things, what the conclusion of Rolle's theorem is. So if we can show these three things of our function, it's continuous, differentiable, and the endpoints are equal, then there is a number we'll call it C in the interval AB, such that, or where, f prime of C is equal to 0. Okay, so let's talk about this Rolle's theorem. Okay, so we're going to have a function, and it's going to be on the closed interval a to b. It's differentiable between the 2 points, and the endpoints are equal. Okay, so we'll start there. We know the endpoints have to be equal, so f of a has to equal f of b. And it has to be a continuous differential function in between. All right, well, I can think of, well, there's three ways to start off. Okay, so if we're at f of a right here, either our function can go up, our function could go down, or alternatively, our function can go straight across. Okay, so let's start with the straight across. If it goes straight across, if it's just a constant, then we see that f prime of c, if we just have some c here, f prime of c is 0 for all of x, right? So maybe actually I won't call it f prime of c, I'll call it f prime of x. All right, the slope of a horizontal line is 0. There's no change in that line. So we fulfilled Rolle's criteria. Let's say we increase our function initially. Well, if we have to end up back at the same point we started, what goes up must come down. And wherever we change that direction, that looks like I did it at C, f prime of c, that tangent line is going to be horizontal. So f prime of c is going to be 0. And then finally, if we go down, like this line right here, well, we know we're going to have to go back up at some point if we're going to go back to where we started. And then wherever we change direction, that horizontal or that tangent line is going to be horizontal. So again, f prime of c is going to be 0. So that's what Rolle's theorem is telling us. All right, so eventually we're going to use Rolle's theorem to prove what this section is called the mean value theorem. But let's see how else we can utilize Rolle's theorem. And we're going to use it to show that a function has only one real root. So we're going to go over to number 20 in our textbook. And it says, show that the equation has exactly one real root. So we're going to show that x cubed plus e to the x equals 0 has exactly one real root. Okay, so that's the problem. So this is what we're going to do. First, we're going to show that there's at least one. First, we're going to show that there's at least one real root. All right, and after we prove that at least one exists, we can prove that only one exists. All right, but the first step is we have to show that there's at least one. And we have a technique to prove that we have a root. So we can show that at least one root exists. I should say at least one real root. And our technique is to use a theorem, and it's the intermediate value theorem, the IVT. All right, so in order to use the intermediate value theorem, the IVT, we would have to show that the function x cubed minus e to the x, so just getting that from the problem, is continuous. And it is continuous, right? Because it's a sum of continuous functions. So that's the first criteria. To use the intermediate value theorem, you have to show that your function's continuous. You also have to show, if we want to show that this is equal to 0 at some point, we have to show that f of x can be negative and f of x can be positive. Okay? And so for the next part, I'll use a darker blue. Okay, we have to show that f of x can be positive and f of x can be negative. All right, well, e to the x is always positive. So I'm going to focus on when x cubed is positive and negative. So I'm going to plug in 0. I love plugging in 0. X to the 0 plus e to the 0 is 2. Wait, oh my goodness. Let me start over. 0 cubed plus e to the 0 is 0 plus 1 is 1. All right, and that's greater than 0. Okay, and then let's see, what else can I plug in? I'm going to plug in just negative 2. And then I'm going to get that negative 8, because that's negative 2 cubed, plus e to the negative 2. That's definitely negative, all right? It's going to be negative 8 plus 1 over e squared, all right, which is less than 1. So this is definitely going to be 0. And you can always take out your calculator to verify, but we can look with our number sense and just know negative 8 plus 1 over e squared is less than 0. So we have that our function is less than 0 and greater than 0. So remember with the IVT, that's important because now 0 is between this negative value and the positive value. So according to the IVT, oops, let me do that over again, since we're going in the negative direction. Here's -2, here's 0. -2 is negative. F of 0 is positive. So because it's a continuous function at some point, we have, or points, it could be numerous points, right? It could go up, down, up, down, up, down, up, down. But there's going to be at least one point where the function crosses the x-axis, and that's your 0. So that's what the intermediate value theorem says. So we just set up the criteria, and so now we can say something like, by the IVT, by the intermediate value theorem, a root exists between x equals -2 and 0. That's what your IVT says. Let's call it A. Okay, so then f of A equals 0. So we're calling this spot, and it could be more than one, right? It could cross over several times, but we're going to call it A. So using the IVT, we showed that there's at least one real root. Now we're going to show that there's exactly one root. And this is how we're going to do it. We call it a proof by contradiction. To show that it's exactly one root, we're going to use a proof by contradiction. So essentially what that means is we're going to suppose the opposite. So let's suppose that there's not exactly one root. Let's say there's more than one root. So let's suppose another root exists. That's the opposite of what we're trying to prove. And we're doing this because it's called a proof by contradiction. We're going to show that assuming this, making the assumption that another root exists, we're going to run into a problem. We're going to run into a gibberish statement. And when we run into the gibberish statement, that means, oh, well, our initial assumption has to be wrong. It's called the proof by contradiction. Okay, so to show that exactly one root exists, we're going to suppose the opposite, that there's another root. So let's call it B. So now we're supposing that f of B equals 0. Okay, so we know f of A equals 0, f of B equals 0. So then f of A equals f of B. All right, and so since we have this final criteria, we can use Rolle's theorem. All right, we're right here. Since we have this final criteria, we can use Rolle's theorem, which is there is another number where f prime of C equals 0. Okay, so then by Rolle's theorem, there is a C in between that interval. Remember that little E sign means in, where the derivative at that point is 0. All right, fair enough. But let's bring our function back. Remember, our function is x cubed plus e to the x. And now we're focused on the derivative. So let's take the derivative. So 3x squared plus e to the x. Interesting. Okay, so why am I saying interesting? Well, we want 3x squared plus e to the x to equal 0, right? And I'm saying interesting because e to the x, is that ever 0? E to the x is always positive, okay? So if you're always a positive number, to get back down to 0, you would have to add a negative number, right? Like 2 plus negative 2. But is 3x squared ever negative? It's always positive. All right, another way of saying this, if we put e to the x on the other side, we can see it in a different light. So subtract e to the x from both sides. So two positive functions, right? So a positive function, or 0, I'll give it that, is equal to a negative positive function, so a negative number. So when is a positive number equal to a negative number? Never. All right, so this is not possible. So there's our gibberish statement. So let's go back up. The only reason why we reached this was because we said there was another root. So it must mean that that original assumption was wrong. Okay, so we hit a wall. So this is not possible. A negative number cannot ever be a positive number. Okay, and remember, e to the x can't be 0. So there you go. So this isn't possible. So it's a contradiction. We call it a proof by contradiction. So b cannot be a root. So this shows us that there must be exactly one real root. All right, and then that's that, and that's the proof by contradiction. Okay, so there you go. So that's how we had this homework problem. We wanted to show that there is exactly one real root, all right, so it equal to 0. So first we used the IVT to show that there was at least one. That was chapter 2 material. And then to show that there was exactly one, we supposed there was another one. All right, and then when we assumed there was another one, we could use Rolle's theorem. But then using Rolle's theorem, we found that there is no C where the derivative could be 0. It was gibberish. So it means that our original assumption was wrong. So B was not a real root. Okay. So there you go. So a little application of Rolle's theorem. But the main thing that we're going to do for Rolle's theorem is we're going to prove the mean value theorem. And let me introduce the mean value theorem, and then we'll see what it looks like in words. So again, very visual. So I'm going to draw a graph. So we have, of course, our assumptions that we're holding up for chapter 4, continuous function on a closed interval, differentiable on an open interval, just like Rolle's theorem, and f of a does not have to equal f of b, so we can have something like this, okay? And then, just make up a function. It doesn't have to look like mine. Just, try to draw a function. It could be increasing at first. You can even constant, something like that. All right, so what the mean value theorem says is that if we essentially took the mean between these 2 points, in that case, it's just kind of you can think of it as a straight line going from point A to point B, and then the function is what does all the fun swirly graphs, okay? This line from f of A to f of B has a slope. The mean value theorem says that there's a point C between these points A and B, where the slope of the tangent is the same as this slope M. Okay, and I can see 2 spots. I see this spot, looks like it has the same slope, and then maybe this spot maybe has the same slope. So the mean value theorem says there's at least one point on the function where the derivative is the same as that slope going from the endpoints. And that's the mean value theorem. So let's see how they break that down into words. All right, so let's do our assumptions. Let f be a function that satisfies the following. All right, f is continuous on a closed interval AB. And f is differentiable on the open interval AB. Excuse me, I should say on V. Okay, so that's what we have, that's where we start with for the MVT, mean value theorem. If we can show these two things hold, then here's what our theorem says. There's a number C in that interval such that okay, and I said that f prime of C was equal to, I'm going to go back up to our picture, M right here. But let me do a little bit more information. M is really the difference of X over the difference of Y, okay? So we can pretty clearly see what the difference of X is going to be. It's going to be B minus A. I'll do it in a different color. It's going to be B minus A. And then the vertical distance, remember this is f of B, and this is f of A. So the vertical distance is going to be f of B minus f of A. So that's what our theorem says. Instead of M, we're going to say that f prime of C is equal to f of B minus f of A from those endpoints of the open and closed interval, and then B minus A. Okay? And then there's an alternative format. Essentially, what they do is they take the denominator and they multiply both sides by the denominator. So an alternative form, it's the exact same thing, just cross-multiplied. So f of B minus f of A equal to f prime of C times B minus A. Okay, so we can use either form. All right. So we're going to prove it. And again, we prove it with Rolle's theorem. And we need one additional thing for our proof. So let me, again, just do a quick sketch of everything going on here. So let's redo that. Let's do our function first. So the function I just drew was f. And then we have our line segment from f of A to f of C, or a secant line. And then we're going to define a new function, h. And h is going to be just the distance, the vertical distance, let's see how vertical I can make my line, between f and the secant line. And we're going to call that function h. Okay? All right, so on with the proof. PF is proof. So let's talk about what I just defined. Let h of x be a function defined as the difference between f and the secant line. Okay, and we're going to call that secant line just AB. Okay. All right, so let's do this. So we're calling this blue line the secant line. And I'm going to make an equation of that line down here. And then once we have an equation, then we can subtract it from f. So we need an equation for the secant line. And we're just going to do it using our slope-intercept form. We have 2 points, A, f of A, and B, f of B. I'll just use the first point. And then we already know the slope is that f of B minus f of A over B minus A. And then that's all you need. You need a point and a slope to write an equation of a line. So the equation of the secant line is y minus the y value equal to the slope times x minus a. All right, and so let's solve that for y. We won't worry about cleaning it up too much. We'll just add f of a to both sides. All right. So now that we have that, we can define h of x mathematically, of course. So h of x is going to be the difference between the function and the secant line, and we just called the secant line y. Okay, so it's going to be f of x minus y. So y is f of a plus the slope times x minus a. Okay? And we're going to use Rolle's theorem now. And let me show you why we're going to use Rolle's theorem on h. If we look at h, coming closer to the point A, the difference between the function and the secant line is 0 at f of a. And likewise, if we go closer to B, h gets smaller and smaller and smaller and smaller until the difference between the secant line and the function at point B is also 0. So we're going to be able to use Rolle's theorem. But since we want to be thorough in our proof, we can verify all three. First, h is continuous. Since f and y are continuous, and the difference between continuous function is continuous. All right, and then h is differentiable. since f and y are differentiable, and the difference between two differential functions is differentiable. I'll just say since f and y are differentiable as a shortcut. And then finally, visually, we saw that h of a is equal to h of b. And then if you didn't believe that, we can always plug it in. So we'll do a little scratch work. H of a is equal to, here's our function for h of x, right? So f of a minus f of a, we'll get rid of the parentheses as we go. And then minus that. And then times x minus a, but again, x is a. All right, so this is going to go to 0, right? Because anything times 0 is 0. Then f of a minus f of a is 0. All right, just like we saw visually. And then also h of b. So we can find that really quick. Let's see, f of x will become f of b. And then x minus a will become b minus a. B minus a cancels with the numerator. Okay, and then we're going to get, I'll do an extra line. Well, no, maybe we can just do it. Remember the numerator's in parentheses, so it's going to be f of b minus a negative, or excuse me, f of b minus f of b. And then negative a minus minus becomes plus. So negative f of a plus f of a. And again, that all becomes 0. All right, again, parentheses are important. We don't want to just subtract the first part of the numerator. We want to subtract the entire numerator. And everything cancels. All right, so again, this shows that h of a is equal to h of b. So now that we've shown those three things, we can use Rolle's theorem. So then we can say by Rolle's theorem, there is a number, we'll call it c, where the derivative is 0. Okay. So let's bring back your h of x function, and let's take the derivative since it's differentiable. So this is going to be h prime, we can take the derivative here, it's going to be f prime of x minus a constant. What's the derivative of a constant? It's just 0. And then here, this is again a constant, it's like a coefficient. And what's the derivative of x minus a? Just 1. So h prime of x is going to be equal to f prime of x minus the coefficient of your x minus a. All right. And we just saw using Rolle's theorem that at this point C, this whole thing is going to be equal to 0. We're almost done. We're on our final step. And so now here's the conclusion of the mean value theorem. Let's add this to both sides. So now we're saying there's a C between A and B where the derivative of that C is equal to the slope of that secant line. And then that proves the mean value theorem. Okay, so a cute little proof. And we proved it using Rolle's theorem and a very clever use of H. Okay, so let's see how we're going to use the mean value theorem. We're going over to number 12 in our homework set. In number 12, we're going to verify that the function satisfies the hypotheses of the mean value theorem on the given interval. Then we're going to find all numbers C that satisfy the conclusion of the mean value theorem.